Yesterday, I'll use the mic so you can hear. Yesterday, I received a phone call from Don Rideout, and his dad passed away yesterday morning. So for those of you who are here today, I do have a card in the back, so make sure you sign it for him and we'll get that sent out. If you're at home and on Zoom, I'm sure he would appreciate other cards as well, and you can contact us if you need an address. So, but I was very sorry to hear that information. Anyway, I do see quite a few visitors today, so I'd like to get them to introduce themselves. So if you are a new member showing up today or a guest, if you could raise your hand and we'll get your name. Yes. If you want to come up, it will be helpful.
You want to get mine?
You can if you'd like, then they can see you.
Thank you for offering.
Thank you very much.
Hello, I am Jacob Gray. I am a senior from Ascend Leadership Academy. I am here to ask if anybody would like to help me with my senior project. It is related to how paleontology impacts locally to North Carolina and how I could better show how paleontology affects North Carolina as a whole. And yeah, I'm just excited that y'all allowed me to be here.
Thank you. Okay, any other guests? Come on up. It's exciting to see so many new faces.
Yeah. Hi, I'm Kaylee Ward. I'm a junior at NC State. I am a geology major with a minor in paleo, so that's one of the main reasons why I'm here. And I also found you guys on social media, so I was really lucky that I was able to join.
Well, welcome.
Thank you.
Yes. Any other comment? I suppose I should have said I'm Terry Denny. I'm the club president.
Hey, I'm Bill Howard. I'm a filmmaker and photographer, and I am doing a documentary called Finding Fossils. I live in Wilson, North Carolina, and I have way too many questions.
There are never way too many questions as a former educator. All right, well, I'm excited to introduce our guest speaker today. Many of you have already met Haviv when he was given a grant by the club, and he came and spoke briefly to us at a meeting. But this is Haviv Avrahami. Is that good? And he has been working on a project based on the grant that we gave him, and he's going to report some of that to us. Unfortunately, I sort of had to coax him to come a little early before his paper is published. So there will be a few things that he's going to hold back because he can't really tell us yet. So I said, well, that's okay. We'll just have you back again to tell us part two. Yeah. So anyway, without he's studying at NC State and finishing up his PhD. So I will turn over our meeting to Haviv.
Yes, absolutely.
Could you move a little bit so those boards won't be in the middle?
Oh, sure.
That could be hard.
If you want to, you can go ahead and. Yeah. Yeah, perfect screen. Is that all?
Yes, it is. Okay. Are comfortable?
Yes. I think it'll work.
Screen pictures will be prettier.
I'm gonna see if I can turn off some lights.
Yeah.
That's
That's great. Thank you for sure.
Let's go ahead and share this screen.
Great, that looks good.
Do you guys see the actual slideshow and not my
Yeah,
notes?
we've got it. Thank you.
Awesome, awesome. So
Hello, everyone. Thank you again for having me. I'm Haviv Avrahami, and I'm a PhD student at North Carolina State University, and also a researcher here at on the 3rd floor of the NRC in the paleontology lab. And I'm a student of Dr. Lindsay Zanas. So I've been here in the museum for about 10 years now. I started volunteering in the prep lab. I think back in 2014, and then I've gone out every year with the team to the field to dig up the dinosaurs, and then I continued on through my undergraduate and my graduate, my master's work to continue here as a researcher. So I just want to extend my gratitude again. Thank you guys so much for sponsoring as part of my research. I was really grateful to get the scholarship, and it's been really nice to talk and work and meet all of you guys. So today what I'm going to be talking about is a new species of dinosaur is coming to North Carolina. It's one that I've been working on since I started my PhD back in about 2019. And it comes from a place in Utah that we call the Mustn't Touch It member of the Cedar Mountain Formation. And I'm going to explain more about this area later. But what's really cool about this dinosaur is the first one was found in 2013, actually, by our colleagues at the Chicago Museum. And then every year we've gone back to this area in Utah and we keep finding them. And they're really exceptionally preserved. Sometimes you'll see there's entire skeletons of them. So without further ado, let's get started. And before we talk about this new dinosaur, I just wanted to share with you guys these figures. So these are some of my favorite historical figures from a historical manuscript. This is a paper written about 150 years ago by a famous British geologist and surgeon, John Hulk. And does anybody recognize what these fossils might actually go to? What animal is this? Anybody have an idea? This is actually the bones of Hypsilophodon. Hypsilophodon was one of the earliest dinosaurs that was ever discovered. Right around the same time that we had the first dinosaurs, which was like Iguanodon and Megalosaurus in Britain. And the Hypsilophodon is among those really early dinosaurs and dinosaur discoveries. And what's really cool, two things with this figure is that one, you can just see how even 150 years ago, how amazing the scientists were at documenting morphology and characterizing shape and creating figures. I mean, these are still extremely useful to us. And in many ways, they're better than figures that were made in the 70s or 80s. They're better than photographs. So even back then, they had a really keen eye, and they were really invested in documenting the shape of these animals and their bones. But they didn't get everything right. Like if we look at their reconstructions, this is what they thought Hypsilophodon looked like. And as you can see, it's very lizard-like. If you've ever been to any historical gardens in Europe, you can see a lot of their life-size reconstructions and creations and things that they had. And they're always very lizard-like, low to the ground. And we know now that they are much more upright and bipedal, that they had like a bipedal stance, and they weren't so low to the ground. They were faster moving, and they were probably running around a lot and stuff. So the other thing I want to mention with Hypsilophodon is that even after 150 years, there's still so much we don't know about it. And namely of which is we really don't know where it and its group of relatives, how they are related to each other. So we really don't have a good idea of how it fits into the family tree of plant-eating dinosaurs. And I'll show you some more figures on that in a minute that explains it better. But let's start with looking at some of the more popular groups of plant-eating dinosaurs. So for anybody who doesn't know, there's really like three main groups of dinosaurs. There's the carnivore dinosaurs, the ones like T-Rex and Velociraptor, and those are the theropods. And then there's this little smaller section that are kind of closer to the theropods. Actually, it's the long-necked dinosaurs, the sauropods. They were plant eaters, but they probably were closer to the theropods in their origination. And then the other 50% of the pie chart, other 50% of Dinosauria is the ornithischians. And those are mainly the famous plant eaters that we're all aware of, right? So these are some of the more charismatic and well-known members of that group of Ornithischia. And for the longest amount of time, and you've probably seen some reconstructions in books and things like this, is we've thought that they're may be somewhat related to each other this way. Like this is the early kind of basic family tree of how we've reconstructed their relationships. But in reality, when we crunch the numbers, when we run the statistics, and when we really look into it, we realize that what we actually have is something that looks more like this. So in the study of evolutionary relationships, we call this thing right here the dreaded polytomy. And basically, that's not a good thing. A polytomy is not a good thing because it's not a reflection of reality. It means that we don't yet quite have a resolution yet to figure out who exactly is related to who. So as you can imagine, this is quite a challenging undertaking to figure this out, because there's so much that goes into figuring out a family tree, and we don't have genetic data like we do with modern animals. And I'll explain more about how that process is done in a minute. But so this is part of my job right now, is figuring out how to reconcile and construct this family tree, reconstruct it in a way that's a reflection of reality. And this is difficult. I want you to imagine that you're going to a family reunion, but it's not your family, it's your friend's family reunion. Walk through the door, and everybody except for you gets amnesia. So nobody knows anything, and it's your job to figure out how everybody is related to everybody else. And this would be a nightmare, right? If we use my family as a case study, right? This is my family, we're very diverse. And if we zoom up here, would you ever believe that this guy is my cousin, this guy's my uncle, and somehow this weirdo is my brother? So if we go back to that dinosaur family tree, the reason that we have this polytomy is that if we follow all those branches down the line, we go to that origin point, what we get is a collection of dinosaurs, which actually includes Hypsilophodon, which are these really small-bodied, early diverging, ancestral plant-eating dinosaurs. And they've been lumped into a number of different designators. Sometimes they've been called ornithopods, but the problem with the term ornithopod is that it also includes these large-bodied hadrosaurs, some of their early relatives. They've also been called neo-ornithischians, but that's also too broad of a term because it includes some of the early ancestors of ceratopsians and the armored dinosaurs and stegosaurs. And they've also been called hypsilophodontids, trying to tie it back to that original Hypsilophodon body type, but that's also not so good because it's making an assumption that all of them are attached as Hypsilophodon is the linchpin to that entire group. So what we really need is a term that we use sometimes in evolutionary biology called a paraphyletic term. It's similar to what we call our bugs. It includes some members, but not other members. So like bugs are an example of this. We'll say spiders are bugs, and millipedes and insects, and land-based arthropods like roly-polies or crustaceans, but we don't call shrimp bugs or lobsters. We do the same thing for the word crabs and things like that. And our ancient ancestors, they used to call dolphins fish, whales fish, because they look similar. So it's kind of a word that describes a shape of a body plan. And so I've been toying with different, this is what some of them look like. This is those neo-ornithischian groups, right? And, so yeah, you can see that they probably were covered in a large density of feathers. But these wouldn't have been bird-like feathers. They would have been much more like the downy feathers of like a baby chicken. They're called like early proto-feathers, a lot more fuzzy, like a plushy toy. And they probably have areas also that were bristly. So we found some examples in China of that they seem to have integument that is almost porcupine-like. But the term we need to describe these animals really just gets to the core of them. What they are, at the essence of what they are, is they are small-bodied, early diverging ornithischians. That's the essence of what they are. So for the rest of this talk, I'm going to be calling them that. This is a mouthful, so we're just going to shorten it and abbreviate it as SPEEDOs for short. So if we look at their skulls up in all together, we can see how diverse and amazing the different shapes and sizes that they took. So this was an early picture I made when I first started my dissertation. I wanted to get all the speedos up together on one page so I can put it up on my wall and just kind of look and try to understand all the differences. This is a really helpful method for doing comparative work. And it's not an exhaustive list. There's a lot more that could go into this. And it's also, it includes the Tenothosaurs and stuff on the right. But this is just to give you an example of how diverse and dynamic their morphologies are. And then, as you can see in the middle, that's the new one that's coming. It's pixelated out. I'm so excited. I can't wait to show you guys when it actually gets here, what it really looks like. But you can see it's doing some wacky stuff. And yeah, it's even better to look at these in 3D rotation. So these are a number of different Neornithischians that are spinning in rotation. As you can see, that's our own famous willow in the top left, Thespelosaurus neglectus. But then there's a number of other ones all over. So and yeah, so they're a really cool and underappreciated, understudied group of dinosaurs. So I want to focus in here on a group of speedos that we actually are starting to have some better resolution on. And by that I mean that we are starting to get a better idea of how they are related to each other. And these are the orodromians. And different studies recover a different number of orodromians in the group, like in the clade as a collection. Sometimes some studies will have them, some members off. There's 3 of them that are definitely orodromians, and that's Zephyrosaurus, Orodromius, and the Capyurus orodromian. And then these other ones are sometimes put into those groups. But they're globally distributed throughout North America and Asia. So not globally distributed, they're distributed only to North America and Asia. But the 3 orodromians that are definitely orodromians they come from North America, and they seem to be endemic. They seem to originate possibly from North America. And so let's zoom in here on the new one. The new one is this one. This is the Mustn't Touch Speedo. And it comes from Utah, like I said earlier, and it comes from rocks that are about 100 million years old. So if we look at North America today, this is the map that we're familiar with, right? This is our current present day North America. And then if we rewind the clock to 65 million years ago, this is what it looked like right at the end of the period of the dinosaurs, right before that asteroid came and annihilated all the non-avian dinosaurs. This is when T-Rex and Triceratops were walking around the earth. And one thing that you can see that's probably pretty charismatic is that there's that big inland seaway. This is the Western Interior Seaway. And this is as it was starting to retreat away. It was small here at this point. But if we rewind the clock back another 30 million years to right in the middle of the mid-Cretaceous, you can see that this seaway was huge and it bisected all of North America into basically two different continents. There was Laramidia to the left, and Appalachia on our side to the east. And so Utah during this time was right on the coast of this intercontinental seaway. And it was a really interesting time for Utah because what was happening is that you had the subduction of the Farallon plate going underneath North America's western coast where California is. This was kind of the early remnants of what we might think of as the Juan de Fuca plate and the things that causes the earthquakes. Back then it was subducting under North America. So you had the orogeny event of the ancestral Rockies. They were pushing back up and they were creating lots of volcanism too at that time. And what that caused is that it caused the, on the other side, the leeway side of the mountains to form a basin. So that's why the entire continental shelf was starting to go down and form a bulge where all the water collected. And because there was so much volcanism also at that time, and it was a mountain building event, you had a massive amount of erosion on the mountains. And then all that sediment was just coming down the mountains and flooding into this floodplain. And so you have so much deposition, and this is how fossils form, right? Because the rate of deposition of sediments outweighed any kind of erosional effects of the floodplain. And so things would just get buried and buried and buried in this volcanic sediment. So if we look at it in animation, This little area, this little strip of sediment that is highlighted in red right there in Utah, that is the mustn't touch it. That is the rocks that are outcropping that we can go to nowadays and walk around and see and look for the dinosaurs. That's where it's exposed on the surface. Oh, thank you. Yeah, I got a sore throat. Thanks. So the sediment here, because of it's a lot of volcanic ash. I said it was coming down. So I like to imagine that the mustn't touch it looked something like this. This is my my digital reconstruction of the environment. And so one thing you'll notice is that the water on the right is supposed to represent the intercontinental seaway. It's the floodplain environment. And then in the background, we have the ancestral Rockies, and that big plume of smoke coming up is supposed to represent the volcanism that's happening at that time. And one thing you'll also notice is that it's dominated by mangrove trees. So we think that it was very similar to what you might think of as the Florida Everglades as an environment. In fact, our colleagues, our geologists have reconstructed it recently as the closest likely analog, modern day analog, is probably the coast of French Guyana. It's just a really long floodplain with lots of rivers and lacustrine environments. So that's what it looked like back then, but this is what it looks like now. This is the mustn't touch it now. It's very different. It's very dry. There's no plants. It's just a barren desert. And this is the mini troll locality. So this is actually where we got one of those new speedos that's coming. This is probably the one of the best sites that we have. And you can see that inside of that jacket there, that white thing, there's two individuals that are kind of bundled up together. We think that they were forming burrows. We think that these animals were burrowing underground. And that's part of the reason that they're possibly being preserved in such a high relative abundance compared to everything else, because they were doing the hard work for us. They were going underground, and we think their burrows were collapsing in them sometimes. So the material here, like what you see, this is when the mustn't touch it sediment is dry, and it's easy to work. It's super soft when it's dry. It's such a nice contrast compared to the bone, which is really, really dark and black. So it's easy to see things. But the catch is that when it gets wet, it becomes a nightmare because it's the same substance that we make cat litter from. And so when it starts to rain, this is my fiance, and when it starts to rain, it gives us hobbit feet. So, and it just gets everywhere, and it's super sticky, and it makes driving a total nightmare. So this is after a torrential downpour, and we're trying to drive to one of our localities. But as you can see, we're driving nowhere. So.
And when you say we are saying NC State, is it NC State?
It's through our the third the paleo lab here. So a lot of times there are NC State students that will come out with us. And we do have a class that happens every other year where we bring a bunch of NC State students, but most of us, it's our core team that are bringing fossils to this museum. So if we go back to this this picture, and people often ask what exactly, like how we get the dinosaur out of the bone. Many of you are probably actually familiar with this process. But we don't pluck the bones directly out of the ground like they used to maybe back in the 1800s and stuff. What we do is we use plaster cement. We cover the bones in the delicate areas with toilet paper, and then we take burlap, basically what we put rice and coffee sacks into. We take that burlap and we smother it in cement, plaster cement, and then we cover it over. So this is what it looks like in a different locality. This is our New Mexico site. And this is kind of how that process goes. And the music is the most important part. Yeah. And so once that hardens, it becomes really hard, and we're able to flip it over. And jackets like this are small enough where we can just put them in our backpacks. But if they're bigger, like at the mini troll one, we have to work together as a team to carry it out. So this is what we do when it's too big for only one person to take. We put it on this long stretcher thing. It's kind of like a surfboard with handles, and we carry it all the way back to our camp. So in this case, our camp is about double the distance from that tree line. So it took us about an hour, I think, hour and a half to get back to camp maybe. And it's quite a haul. But sometimes the fossils are even bigger than this, right? So if you ever looked through the window of the NRC recently, you've probably seen that gigantic Triceratops skull that's under preparation. And that was found in the same locality as this. This is our dueling dinosaurs region. This is the Hell Creek. So this is where we find really big fossils. And not far from here was our Triceratops skull. So when we got that out of the ground, we had to get in, we had to ask for a little extra help. So yeah, we had to get a helicopter. But it ended up making it back here safely. So. All right, so if we go back to the mustn't touch it Speedo, one thing that's really cool is that the mustn't touch it. We've had a series, a number of geologists. So one of our closest colleagues is a geologist who's been working on the geochronological age dates of the mustn't touch it. So what we do is because of all that volcanic activity, we get a lot of zircons that are coming from the volcanic activity, and we get really refined ash beds that we can track all the way across the formation. You can go into these ash beds and you can get little tiny pieces of zircon, and you can test the ratios for uranium to lead, and they act like atomic clocks, and so we can get really precise age dates for the times between these ash beds. And recently we've gotten these really high resolution age dates between ash bed 2 and ash bed 1 is only about spans a 13,000 year window. So this is some of the highest resolution we've ever gotten out of the Mesozoic. It's really, really amazing, and it's going to set the stage for a number of really cool studies in the future, maybe about like the grade of short-term evolution over 13,000 years in changing environments or seasonal patterns. There's so much we can do there, right? We don't yet quite have the sample size ready to do that now with the Speedos, but at the rate we're finding them, possibly we could do things like that in a while. So when we got the mini troll jacket out of the ground, it looked like this on the right. It was a big jumble of bones. And so before we started preparing the bones out and kind of pulling them out of section, we wanted to collect that data so that we could see if we could identify patterns of preservation and taphonomy, or see if we could find out which bones went to which individual. So we took it to the vet clinic here in Raleigh and we CT scanned it, and then I had a student of mine segment out a lot of the bones. We worked together to segment out the bones and identify them and give them different color codings. And what you can see is that in this one, there's partial articulation. There's a foot in there that is kind of preserved in articulation, and it seems like these two individuals may have been either face to face or butt to butt in the burrow. Is that's what I think. I think that they seem to be right next to each other, either facing each other or facing away. Not quite sure though. There's still more work that needs to be done on this in the future. But what's really cool is that after we found this site, about 2 years later, we found our most exceptional site belonging to this new animal. And it's a fully articulated postcranial skeleton, which you can actually see in the window if you go upstairs on the 3rd floor. And this is the linchpin of the new dinosaur. So you can see this VFX rendering of it. In a minute, you'll see all the bones pop out and highlight. So this is really cool, right? Where you can, what you're looking at right now is the stratigraphic bottom of the animal. You're looking at it as if you had the animal on a coffee table and you're looking up at it from below the glass. So up here where the 2 blue bones are, the 2 light blue bones, those are like the bicep bones, the humerus. And so what happened, it seems like it was preserved where it was just, but I think the burrow, if it was in a burrow, it collapsed in a burrow, it just got flattened like a pancake. And then if you move down the column, you can actually see that its hips twist. And so what we're looking at here on the right side is actually its foot that's curled up close to its body. That's its death pose. So really interesting stuff. And I'll talk more about this guy in a little bit. Early on, what we did though is we wanted to figure out how old these animals are, and the way that we figure out age in dinosaurs is by doing a process called histology. So this is a this is a histological section of a turtle shell. I'm just showing it to represent what we do. Well, we take the bone and we cut it, and then we polish it down to the point where it's as thin as paper. And when it's that thin, we can put it under a microscope, a special called it's a polarized microscope. It has the same lenses that are in our sunglasses, and they control the way that light waves move so that we can see particular features in high resolution. And when we did this with the new dinosaur, we were able to count the growth lines like tree rings to get out its age dates, because there's seasonal variation and they have periodic changes in how they grow over time. And so we did that, and we realized that these animals were about 4 to 5 years old, and they seem to be subadults, possibly teenagers. They're sexually mature, but they haven't reached full adulthood. And it's a little bit different in archosaurs, right? Mammals, we stop growing at a certain age. In archosaurs, they had indeterminate growth, so they keep growing throughout their entire lifetime, but they slow down once they reach like full skeletal maturity. And it doesn't seem like these guys have reached full skeletal maturity, so they possibly could get a bit bigger. And some of the new materials that we pulled out recently do seem to show that they could get quite a bit larger. So to go back to the construction of family trees, this is orodromines in the blue with the blue bars. And for the longest time, that's what we thought this new animal was going to be. And so orodromines are really closely related to their sister group, Thespelosaurines. And this is what includes willow. Willow is a Thespelosaurus. And so what you can see is that it seems like the orodromines were here first, and then out of nowhere, Thespelosaurs just show up at the very end, and they replace the orodromines, but they show up out of nowhere, and they make it to the very end of the Cretaceous. That's what seems to be the pattern of what we see here. And so our new page that's coming out is probably going to shake this up a little bit. But the way that we do that, okay, so the way that we create family trees of dinosaurs is very complicated. It's like if you've ever been to the doctor, you have to do the questionnaire where you do like yes or no, I've done it, I have this, I have that. It's like 30 questions, and it's usually a yes or a no. Basically the same thing we have to do with dinosaurs, but instead of like 30 questions, it's now up to like 400 questions. And we do it over, we have to do it for each individual species. So we're doing it over like 80 taxa. And as you can imagine, in paleontology, not everything is complete. So some of the answers are answered, some of them are unknowns, because some dinosaurs aren't fully preserved. So it ends up creating a matrix that looks something like this. And this is just like 3% of what it actually is, right? It goes far farther, right? It could probably extend to the window. But this is a snapshot of what that looks like. And so we go through here and we code for each one of these, and then we run it through a series of analyses, which I'll show in a minute. But what I've been doing is I've been creating a new matrix for my dissertation work that includes up to 472 characters. I'm combining a bunch of previous matrices, and it includes all these different groups of dinosaurs. And this is all in the hopes of getting a better resolution. So my preliminary analyses are showing some really good success. What I do is I run a series of Bayesian analyses. Bayesian is kind of like an advanced statistical program. You can almost think of it as like, it's almost like machine learning or AI powered. It depends on a lot of computing power. And what we do is we run a series of like 30 million iterations of different trees to see which ones fit the data best. And so in this graph here, in this family tree here, you can see that the areas that are really dark red or orange are the interrelationships that are more strongly supported. So for example, down here in Camptosaurus, Iguanodon, and Tyrannosaurus, basically what that means, since it's so red, is that in all 30 million iterations of the tree, basically, it's recovered as that being a likely relationship. And so this area that's kind of whited out in the middle, that's the new area where we're starting to build up more resolution. But you can still see that, like if we zoom in here, yeah, this is Thespelosaurinae. These are the groups of orodromines and Thespelosaurines combined. We're starting to get up to 80% confidence, which is pretty good for what we're dealing with. But there's still a lot that is unknown. If we zoom back out and we look, you can see that this entire area here, there's still so much life, there's still so much. And so basically all of those animals end up becoming wildcard taxa. You can see Hypsilophodon there, right in the middle at the bottom. So yeah, we still have really no idea how these animals are related to each other. There's some other analyses that we can do. This is called a PCA. It's a principal component analysis. And instead of the matrix, which I showed you earlier, which are just discrete questions like yes or no, or present and absent, what we do with a PCA is we take a series of continuous measurements. These are linear measurements that you can see over here on the left. What we did with this is a scapula bone. These animals have really wacky scapulae. It's their shoulder bones. And they're super sharp. If they were made of metal, you could attach it to a pole and turn it into an axe. So they're really long and thin, blade-like elements. And so we do a series of these measurements across them, and then we plot them all together, and you can see how things are mapping out in morphological space. And so you can see that our new dinosaur up here is plotting somewhere between Eryctodromius, Thescelosaurus, and Orodromius. So that suggests that it's very close in affinity to some of these animals. All right, I'm going to switch gears here now and start talking about some of the really weird parts of this animal's body. So let's look at the dentary teeth. These are the dentary teeth. It's a bottom jaw. And on the left, we can see the side of the tooth that is more close to the cheek of the animal. And then when we move over in rotation to the right side, lingual view, that's the part of the tooth that's close to the tongue. And in most speedos, what they have, that area that's highlighted in blue is called a wear facet. It's where the teeth contact each other when they're grinding plant mat material. And usually in these animals, it is angled somewhat, kind of like a pyramid. But for some reason in our new speedo, they're sheer and they're vertical. They're like 90 degrees vertically oriented. And they also terminate at their base, it's abrupt shelf. So I don't know what's going on here. Sometimes I wonder if it might be related to their subterranean lifestyle, if they are burrowing. Maybe they're eating tubers, maybe they're chewing on roots, or maybe it's just something else in the environment that is demanding their chewing patterns to change. Another really wacky thing is their hips. These guys have really weird hips. In this one animal at the top, this one individual, and it's hip, these are equivalent to our lumbar. In these animals, they fuse this entire sacral column into a long pole that's all ossified together. And in the second and third vertebra of the new muscle toucher guy, there's these deep voids that pierce it laterally. And it's only in this one animal, which makes me think it could be pathological. But there's a lot about it that doesn't seem to be pathological, like the structure of the bone around it, or that it's symmetrical, it's bilaterally symmetrical. So we just don't really know yet what's going on here. Another really wacky thing is its ischia. So these are the bones, if you ever seen a reconstruction of like a tyrannosaur, it has its hip bone, which is that big shield, and then it has those two bones, one that sticks forward and one that sticks backwards. In the plant-eating dinosaurs, none of them stick forward. They both stick backwards at an angle and they run in parallel. And this is the bone that's on the top. And what you can see in our new speedo is that down the shaft, there's this area that gets really inflated, almost like you had a turkey baster and you just shot it up with a turkey juice or something. It's all inflated like a tubercle. And it's really weird. I don't see this feature on any other speedos. And actually the closest that I found is a muscular attachment that we see in crocodiles and actually tyrannosaurs in some theropods, where they get a tubercle here. It represents a muscle attachment point for a muscle that connects to the tibia. So this is another reason that I think maybe that they are doing some biomechanical constraints or adaptations for burrowing. I think these animals are probably burrowing with their feet predominantly. That's what we see in a lot of modern bipedal animals like Jerboa or springtails, or the bush turkey in Indonesia. They do this system where they go into their burrow and they use their tiny hands or things to scrape away parts of the walls, and then they they collect the sediment and then they get into a stance and they use their powerful leg kicks to just shoot the sediment out. That's what the Jerboa do. And so that's what I think that they might be doing here. And I think that they're probably using their feet a lot. Another really weird thing is if we zoom in here on the pubes, we can see that when the two pubes come together and they meet in the middle, I've never seen this before on any other ornithish game, but they fuse. They become one element. They become one shaft at the pubis, and this is a really weird feature. Okay, so to wrap things up with this part of the talk, this is go back to this picture. This is kind of what I think the muscle touches speedo may have looked like. We've got some other reconstructions. This is still a work in progress, but this is something I've been rendering, and we can actually zoom in here and see them closer up. Yeah, they do have a beak. They have we think they have a keratinous beak at the top. Okay, so for the second part of this, before we wrap up, and I'm good on time, right? I think. Okay, cool. I just want to show I'm giving a talk later this year on some new methodologies that I'm creating for creating surface scanning. So, like I showed you earlier with John Colt's work, it's very beautiful back in the day, and they're really capturing morphology and osteology. And I think they would be amazed that we can do that nowadays in full 3D. Like a Harry Potter picture where things are moving around. So traditionally, the way that we did this kind of work is for the longest time, we just took a DSLR camera and take a bunch of pictures in rotation around an element. Then you do tons of data processing on a computer. And sometimes these processes can take hours to days in the past to get even one model. And then, but the technology's come very far in the last few years. Pointing out, thanks to the industry and commercial things, we have commercial scanners that can produce some really exceptionally high detailed scans, but they are also exceedingly expensive. But the thing about it is that we don't really need those commercial scanners all the time because our cell phones that are in our pockets are extremely powerful machines, and they are getting better every year exponentially in what they can do. And so every time you take a click of your phone, you're capturing a swath of data, right? So our iPhones, they capture a ton of information, not just pixels and details like that, but they're sorry. I forgot to turn my phone on. It's a good sound. So yeah, our iPhones are taking a lot more information than just images, and this is how we're able to do so many camera effects, take blur and things like that. Even with the upcoming iPhone 15, the sensors are just getting absolutely amazing, and the technology is getting smaller and smaller. They're starting to incorporate the use of AI and things and stuff, and so they're becoming really, really powerful. Every time you take a click of your cell phone, you're collecting more than just the image data. You're also collecting depth maps. Your phone is also shooting out LiDAR and laser blasts in the infrared range and in the UV, the ultraviolet range. And your camera is also taking information on the orientation of the cell phone in an actual 3D space. And all of this is incorporated into a high efficiency compression format. And so by leveraging all this and a number of different applications on the iPhone, we've been able to collect 3D models of some exceptionally small things. So one thing we're doing for the Dueling Dinosaurs project is we've launched a new program called the Cretaceous Creatures Project, the citizen science project where we send out microfossils from the VD site, and we send it all across North Carolina to different middle schools. And for that program, we've had to create a bunch of learning materials and a bunch of fossil identification guides, because what the students get to do is they get the fossils in their classroom, and then they pick through the material, they find and identify the fossil, and send them back to us. This is how we're able to scale up that process really big and get lots of really cool data. But we had to create a learning module for them. And so this is part of what we got to create. All right, this is on the website for it. And these are all the different kinds of fossils that we can find across Montana. So really cool stuff. Yeah, you can see some mammal teeth there down at the bottom left. And there's some triceratops teeth and all kinds of vertebra and fish scales. And so this is the kind of stuff that helps them learn. And then I've also been fortunate to be able to use a lot of CGI software in the process of making all of this. So I've learned how to use a program called Blender to create some of the animations and that you've seen. So this is one thing that I created for the Cretaceous Futures project. It's supposed to kind of represent a digital environment. And then we can also use this technology to create really advanced and high resolution 3D models of our quarries. So this was a rib shaft of a big Eolambia that came out of a quarry, and yeah. And then you might have heard recently we just published a dinosaur a few months ago called Ioni. It's closely related to this new dinosaur actually that's coming out. So iguanodon. And I forgot there was music to it. Yeah, so I created this 3D model rendering of its skull, and we included this as part of the paper. But we reconstructed this entire skull in 3D space. And then also recently I did a version of I did a rendering for Nat Geo. So it was kind of a version of this, except this is a more whimsical one I did for fun, where I put the Smithsonian T-Rex and Triceratops inside of this cathedral. The video is laggy right now because it's such a big file, but I'm proud of this. So yeah, if you've ever been to the Smithsonian, you might have seen these. They have this on exhibit, and so they put these 3D models freely on online. And but yeah, I think that's it. Yeah, so that's it, and thank you everyone, and happy to take any questions.
What specifically did you use the grant money for?
It just kind of went into the pool of everything. So I took some trips to Europe actually to look at some. I think what mainly I focused it on was my trips to Europe. I went to Switzerland and looked at a dinosaur called Ophneliosaurus. Yeah, it's an earlier one from the Jurassic, and it lived at the same time as Drydosaurus. Yeah, so thank you.
What's the thing we had with that you're showing to the middle school? Was that all done with the iPhone?
Yeah.
That was all iPhone.
So actually, some of them were iPhone, and some of them were a CT scanner we had. NC State actually has one of the most powerful CT scanners in the world. It's called the Zeiss. It can get things in the millimeter range. So before I perfected this method, I had to use that to collect the 3D data. And then we put the textures and the colors on it afterwards for them to kind of designate what part was the enamel and what part was like rough bone texture. So a lot of times we have to put in the shading post-processing, the lighting effects and things like that. Yeah. But some of those fossils are so tiny we use the CT scanner.
How did you get to copyright your method? Since you said you're kind of creating this on your own?
Kind of, I mean, it's also kind of in academia, it's like open source. I'm giving out the workflow I'm giving a talk on in about a month or two. Yeah.
Can you check the chat box and see
Oh.
if anyone's asking questions online?
Absolutely.
Sometimes people will type them in.
Let's see here. Let me expand this.
I think stop sharing your screen. You have to type.
Oh, you're right, yeah.
Yeah, there's not any comments. There's not any questions.
There's any question.
There's not any comments, okay.
Oh, okay.
You just want to be sure we don't overlook.
Like. Let me see how many participants there are.
I think I count 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, nine participants.
Just to get that.
Hey, great presentation. We
It
like the
was.
graphics on the
Fantastic.
small fossils that you're sending around the schools to identify.
Mhm.
Those from the Cretaceous, were they?
Yeah,
Did you get them by screen washing or from the anthills, or where were they from?
actually both. Some of them are from an anthill that's right near site. So I don't know if you've heard of Clayton. He's the guy who found the dueling dinosaurs. And then that's who we purchased them from. So we go out to his land and then areas around there to collect the bulk material. And then we bring it back and we do screen wash it here. We have a shed out in our offsite area where we screen wash all the material. And we distill it down to where it's just some of the big rocks and the fossils. And it's all Hell Creek material. Yeah.
Say a novice like me wants to scan a vertebra, 360-degree view. Is there an app that I could use on my cell phone?
Yeah, I recommend downloading a free app starting with it. It's pretty easy to use. It's called Scaniverse. If you're on the iOS platform, if you're on iPhone. Scaniverse is made by the same company that created Pokemon Go. And so they have powerful processors that are used as you upload your images to the cloud and then they're processed in the cloud and then they send you the downloaded file. So that's the one that's free, probably the most popular 3D scanning app on both the Google Store actually and on the iOS App Store is called Polycam. And that's probably the most popular one. Also, I think it's $20 a month. Some of them are $7 a month, some of them are $20. But there's some other free ones. There's a lot out there. So you just have to look at like 3D scanning app and experiment.
This is a basic question, but often in books or on television, you'll see dinosaurs drinking out of streams. And the waterway that came through North America, was that brackish? Was it salt water? Was it partly fresh water? I've always wondered.
Yeah, it would have been saltwater because it's such a large inland sea and it's connected. The water that was coming down from the mountains, though, like through the streams and rivers, they would have been probably fresh water, and then they meet at the ocean where it becomes brackish. Well,
Thank you.
Thank you.